Imagine this. You've got exactly 20 minutes before your Cambridge Physics 0625 mock exam begins. The invigilator's pacing at the front of the hall. Your palms are getting sweaty. You flip open a practice paper for one last desperate check, and boom, you see something absolutely terrifying. A giant red 0. This is the exact mark a real student just received on a critical 4-mark electricity calculation. 4 marks, just gone in an instant. And honestly, that's enough to drop them right down across a critical grade boundary.
So where did they go wrong? Well, here's the wildest part. It wasn't a lack of knowledge. They actually knew the physics. It was a fatal flaw in their exam strategy. They rounded their numbers way too early in the calculation, and they completely forgot to write down their units in the final answer. The examiner literally had no choice but to tank their score.
Section 1. The fatal circuit mistake. Okay, let's dive right into this and build your ultimate survival plan for basic circuit setups. Because losing marks on fundamentals today? Yeah, that is simply not an option. First things first, let's lock down component symbols and meter placements. It sounds simple, but so many people mess this up. An ammeter? Always in series. A voltmeter? Always in parallel. If you draw a circuit diagram and get these current paths or meter locations swapped around, you're looking at an instant fail for that question. It basically tells the examiner you have a fundamental misunderstanding of how current and potential difference actually work.
To absolutely guarantee you hit those marks, you need a bulletproof system. Check out this 4-step framework we've designed specifically to nail those Cambridge command words. Step 1. Identify the underlying concept. Step 2. Grab your evidence or data directly from the circuit diagram or the table. Step 3. Apply your scientific reasoning. And finally, Step 4. Package the whole shebang using precise examiner wording. You master this loop, you master the exam.
Section 2. Series versus parallel traps. All right, let's escalate the stakes a bit. Because ordinary revision usually completely falls apart when we step out of simple series loops and enter our first major trap area, parallel circuits. And this brilliantly illustrates exactly what goes wrong. Just look at this flawed student answer. Current splits up and voltage flows through. I mean, it kind of sounds right, but physically, it's complete nonsense. Voltage doesn't flow. Now compare it to the perfect top band response. Current divides among parallel branches, potential difference remains constant across components. See the difference? That terminology-rich response is exactly what the mark scheme is begging for. Okay, let me put my strict examiner hat on for a second. Let me tell you exactly what destroys marks on circuit explanation questions. It's the red pen checklist. We're talking missing units on your final values, super vague explanations like electricity goes there, plugging the completely wrong variables into your equations, and messing up field patterns around wires. Seriously, guys, do not give the examiner a reason to bust out that red pen.
Section 3. Power and energy calculations. Okay, we are officially in high-stakes territory now. Listen closely, because in a moment, I'm going to show you the exact examiner clue that changes calculation answers completely, literally pulling you from a 0 straight to full marks. But first, you absolutely need the framework that makes that clue entirely obvious.
Let's test your eyes with a parallel circuit power calculation. If a student calculates the intermediate current as 1.33 amps instead of using the exact fraction and then squares it for their power calculation, look closely. Can you spot the early rounding error before it cascades into a total disaster? That tiny, seemingly harmless shortcut just cost them the final accuracy mark?
Here is the formula for absolute success, and that examiner clue I promised you. Before you even think about touching your calculator, write out the substituted values directly from the source data alongside their exact units. If you write down the raw substituted values on the page, you instantly secure the method marks, even if your finger slips on the calculator later on. It's a total game changer.
Let's anchor that calculation right back to the core physics concept. Power is defined as the rate at which electrical energy is transferred by an electric circuit. Remember, this isn't just some abstract mathematical formula on a page, it's a physical reality measuring exactly how fast energy is moving. Lock that definition into your mind. Section 4. Data and practical investigations. All right, moving beyond the theoretical math, we hit the practical elements of the syllabus. And I'll be honest, this is where you're going to face the highest cognitive load in your exam. You aren't just reciting facts anymore, you're actively analyzing real-world, messy data.
So you've got to be aware of these specific practical traps. Flipping your independent and dependent variables on your graph axes, classic mistake. Offering super weak practical improvements, like just writing down, "do it more carefully," will literally earn you 0 marks. And finally, making massive, grand conclusions that aren't actually supported by the data table or the graph right in front of you. Every conclusion you write must link directly back to the provided evidence, no exceptions.
Section 5. Essential Circuit Safety Checks. Now, the absolutely crucial point here is that Cambridge loves to test your holistic understanding. A massive favorite trick of theirs is taking a high-level energy calculation and mashing it up with real-world safety checks into a single, terrifying multi-part question.
Check out the difference between a superficial guess and actual scientific reasoning here. A weak safety check just says, look for broken wires. I mean, sure, that's true, but it's way too basic. Now look at the strong, scientifically reasoned check. Ensure current does not exceed the fuse rating to prevent overheating. See what happened there? That uses our 4-step framework perfectly. It applies the concept of current, references the specific fuse rating data, and gives the actual scientific reasoning of preventing overheating. Nailed it.
Before you even think about turning the page to the next question, I want you to mentally run through this rapid-fire checklist. Correct units? Yep. Appropriate significant figures? Usually 2 or 3? Yes. Graph scale checked? Uncertainty noted? Safety reasonableness verified? If you can confidently tick all of these off, your answer's pretty much bulletproof.
Right, let's put everything we've talked about to the ultimate test with a really complex, multivariable problem. Imagine a high-power heater is suddenly added in parallel to an already overloaded circuit. What exactly happens to the total energy transfer of the entire system? And, based on those principles we just covered, what is the exact, specific safety risk involved here? Really think about how parallel resistance affects the total current.
To properly crack that problem and articulate it for full marks, you're going to need a top-band evaluation framework. The mock survival plan continues next. So, as you head into your mock exams, ask yourself, if that high-power heater trips the system, is your answer going to cost you a single mark, or will your scientific reasoning be absolutely bulletproof? Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Let's get that top-band framework locked in. See you in the next one.